Hi Year 10, I thought we'd continue doing the start of these videos face to face, or as face to face as we can go. I'll do the start questions, introduce the topic, and then we'll head back to the regular lesson as last time. So our first question is why could antibiotics not be used to treat COVID-19? Okay. 2. How many stages of testing would a medicine need to go through before it was made available to the public? So both these last two questions would have been in our previous lesson, the one on medicine, so if you have no idea what I'm talking about, either go back and watch that or make sure that you're doing these lessons in the right order. 3. What does a vaccine contain, or what do vaccines contain? So this is thinking back to our previous week's lesson. 4. State the equation for Newton's second law. This is going back a wee bit further, right back to the start of lockdown. Our first week together, we looked at Newton's laws and I gave you an equation for Newton's second law. 5. How can we test the pH of a solution? So going back a bit further still, back to when we were in school. And then finally, going way back to 2019, what do we call it when a substance goes straight from the solid state to the gaseous state? So skipping that liquid state in the middle. Good, so we'll go through the answers then. So classic question is why antibiotics wouldn't be used to treat a different type of disease, to bacteria. That's the key. Antibiotics can only be used to treat bacteria. So it wouldn't be effective against coronavirus because it's a virus. Okay. Medicines need to pass through 4 stages of testing. So that's computer testing, human tissues, animal testing, and then finally clinical testing, which is human trials. Pathogens contain dead or inactive. Vaccines contain dead or inactive pathogens. Just really important you remember that. A couple of easy marks there. Newton's second law is force is equal to mass times acceleration. There are a good few ways of testing pH. You could use a pH probe, which would be most accurate. You could use litmus paper, or you could use universal indicator and get that nice colour change. And then finally, going straight from solid to gas is called sublimation. Good. So today we are very much carrying on with what we looked at last lesson in terms of medicines, and we're looking at this collective way of killing pathogens, killing bacteria called antimicrobials. And this is things like Dettol, bleach, plus a whole range of different medicines and different solutions that can be used to kill bacteria and other pathogens. Some of these are naturally occurring, things like garlic, and it's naturally antimicrobial, and there are chemicals like the ones I've mentioned, but also things like vodka, other alcohols have a natural antimicrobial effect, that is, they kill pathogens. So we're going to look at how we can test these today, test to see how different microbials work, how effective different ones are, and as part of that we're going to look at how we grow pathogens, how we grow bacteria, so that we can then see how easily we can go about killing them. So we'll go back over to the regular slideshow and I'll talk you over some bits and pieces. Okay, so if any of you have ever used a substance like Dettol before, you'll have seen that on the bottle it says something like kills 99.9% of germs. And really what we're looking at today is how they go about being able to make that claim and how we go about knowing that these are effective and how other medicines are effective as well, other antimicrobials. So let's start by knowing what an antimicrobial is. It is just a chemical or another substance that will kill microbes and pathogens. So an antimicrobial is something that we use to clean or disinfect or to sterilize substances, but also it can be medicines that we take ourselves to fight infection. So antibiotics that we looked at last lesson would be an antimicrobial. Dettol that you use to clean surfaces with, to clean floors with, is an antimicrobial. It'll kill any pathogens, it'll kill other bacteria. Indeed, it's effective against killing the
coronavirus, for example. There are also naturally occurring antimicrobials like garlic is really effective at killing a wide range of different pathogens and viruses. And alcohol is a brilliant antimicrobial. Alcohol hand wash works because it kills all types of pathogens and diseases. And the more concentrated your alcohol, the more effective the antimicrobial is. So Smirnoff of vodka is particularly good because there's lots of alcohol within it. Okay. How is it that we know that these are antimicrobial? How is it we know they kill pathogens, viruses, other things? We know because we're able to grow bacteria, grow other pathogens, and then see what happens when we introduce these things to it. We can see those bacteria, other things die. So this here is a Petri dish with bacteria growing on it. The glass is your Petri dish, and all of these different blobs, different coloured, horrible looking things are different types of pathogen. And they are growing on a jelly-like substance called agar. It is pretty much just plain jelly, and you can add nutrients to it, add things that bacteria, viruses like in order to grow quickly and strongly. And we'll look a little bit more at that later. So what we do is we grow these pathogens, and then we're able to introduce the antimicrobials to it and watch to see whether their growth slows or indeed whether they start to die. So my pathogens here, if I added a lump of garlic to this, you'd see that some of them, not necessarily all of them, would die. If you added a load of vodka to it, you'd find that more of them died because it's a more effective antimicrobial. Okay, so growing pathogens, growing microbes like this can be quite a risky business, and so you need to take certain precautions in order when doing it in order to be safe and make sure you're growing just what you want to grow. Okay, so when growing pathogens, we use something called aseptic techniques, and aseptic is just another word for sterile. We want to make sure that when we grow that pathogen, we only grow the thing that we want, and we don't inadvertently grow anything else, because that means our sample is contaminated. We might be growing something that's dangerous to us or to others, or it might just mean that our results are no good, because instead of looking at the effect of a medicine on one bacteria, we're actually looking at it against lots of different ones. So aseptic techniques might sound very sciencey and complicated, but it really isn't. It's common things that we do in order to sterilize surfaces, equipment, and you'll have heard of some of these before. So one is using ethanol to clean down all surfaces and all equipment. So ethanol is pure alcohol. It's as close as you can get to pure alcohol, and it will pretty much kill any pathogens out there and sterilize anything. It's incredibly effective. It's what lots of hospitals use to sterilize work surfaces and medical equipment. It will just destroy any pathogens there. Okay, so you spray this down, and that makes sure that all surfaces are cleaned. Good. And then what we use is a Bunsen burner, and whenever you're pouring your agar and trying to grow your plates, and we'll have a little video of what that looks like in a minute, you have a Bunsen burner on. And what this does is it means all the hot air rises above your work surface, and it takes any pathogens in that air up with it, and it creates like a protective bubble in which you can work in. And then you can put all your equipment into that Bunsen flame, heat it up, and again that kills any bacteria, any pathogens, because you are causing those enzymes to denature, and your pathogens shrivel up and they die. Okay, and then for you yourself, it's about washing your hands. It's about using any personal protective equipment that you might want to use, such as face masks. Lab coats are really important, and washing your hands is mega important. When you're handling these Petri dish, this agar, all your equipment, you don't want any of those pathogens that we have on us all the time to rub off and to inadvertently grow them. We want just the pathogen that we are after. Okay, equally, covering your face, covering your nose stops you exhaling and blowing a load of different pathogens on it. Dependent on the importance of what you're growing really depends on the level of equipment you require. If you were in school right now, we'd be doing this and we wouldn't be worried about using things like face masks, but we would all be washing our hands and wearing lab coats. Okay, so all of this means that when we grow our pathogen, instead of getting lots of different coloured spots like we do here, we're much more likely just to get one colour, and it will cover the whole of the agar, the whole of that jelly, which is more what we're after, because then we can see how effective antibiotics or different antimicrobials are at killing those bacteria. Okay, so this plate here would be entirely full of this bacteria. All this scratchy bit would cover the entire plate, except that all these little paper discs here, and that's all they are, little paper discs, have been soaked in a different antimicrobial which has a different effect against this bacteria. And so the more effective the antimicrobial, the bigger this clear zone is around it. The bigger the clear zone, the more effective we can say that that particular antimicrobial is in fighting or killing the pathogen on that plate. Okay, so we're going to watch a little video now of how to go about pouring one of those plates and how to put bacteria on it, and then how that bacteria grows and how these clear zones develop, before coming back here to look at how we calculate the area of these clear zones. Okay, so the first thing you need to do is to clean down your work surface. You'd use something like Dettol and then ethanol. Ethanol is pure alcohol, is the best thing for killing bacteria, any other pathogens. Then once you've done that, you're going to light a Bunsen, and this means that all the warm air rises over your work surface and takes any of those pathogens with it, and then you can clean your hands. It's important to sterilize the area, to use aseptic techniques, so that when you grow your bacteria, you only grow the one that you want. And important in this is sterilizing all your equipment, including this loop, which is what you use to move bacteria around on. So we're going to pick up our bacteria on that in just a second. Okay, you've just got it really hot, so you need to cool it down, and you do that by placing it into this jelly, which is called agar, and agar is what we use to grow bacteria on. And then we pick up some bacteria on that loop from an existing growth, and we just spread it across our agar. And agar is just like jelly, it feels like jelly to touch, and it just supports bacteria growth. Then once we're done with that, it's important to sterilize our equipment again, because we've got that pathogen on it, we've got that bacteria on it, and we wouldn't want someone else picking that up and getting infected with that pathogen. Okay, then it's important to label what you've just done. You wouldn't want someone picking this up later and not knowing what it was, and then sealing it in much the same way. You don't want to get those pathogens out into the air, breathe them in, and someone particularly might pick them up. And then you place it in the oven and allow it to grow. And normally that's at 37 degrees to make sure that they've grown nicely. And when you look at it the next day, you should see some bacteria growth. And then it's a case of introducing antibiotics to that. And we use this fancy machine here, and each of those paper discs has some antibiotics on it. And once you leave your bacteria to grow longer, you'll be able to see that the antibiotics have stopped the growth in certain areas, as this video shows here. The better the antibiotic, the better the reduction in bacteria growth, these clears. Okay, so at the end of that whole process, we end up with a agar plate covered in bacteria with these clear zones on it, and it's these that we're interested in, because calculating the area of these clear zones allows us to see how effective the antimicrobial has been. So that's what we need to go about learning how to do. And this is just a bit of maths, okay? We need to know that a clear zone is the area around the antimicrobial that's clear of growth. You need to know that as a definition, but actually calculating it is just maths. It's knowing the equation for an area of a circle, which is pi r squared, and then knowing that the greater that area, the more effective the antimicrobial, which makes sense. The more bacteria it's killed, the more pathogens that it's killed, the more effective it must be, the better job it has done. So as much as you can look at these and think, well, that one's a bit bigger than that one, to really precisely compare it, because these two look reasonably similar sizes, we need to go and calculate the area of it, okay? So pi times radius squared. Okay, so the radius is from the centre of the circle to anywhere around the outside of it. It is quite difficult to calculate the radius in that way, to do half of it. So what we tend to do instead is calculate the diameter, that whole distance across from one side to the other, and then half it to find the radius. So we're going to have a little look at this example now, and I'll do that on pen and paper, and that'll be us done with the lesson, and you can go ahead and complete this week's assignment. Okay, one note with this is these are always, because you're doing that little bit of maths, they're quite generous in terms of the number of marks available. So learning that equation is really good because you need it lots in maths, and then it's worth lots and lots of marks in science as well. So I'll cross back over to pen and paper now, answer this question, then we'll be done.
Okay, so this is my attempt at drawing out one of these questions. I'm still without a printer, so I have to make do. It will often give you one of these plates with these are your bacteria discs, and this is your clear zone around it. It will normally be labelled, and it might give you a little bit of like preliminary talk about it, but the important thing is it will say compare the effectiveness of two antibiotics, which are A and B here, and it's just about really knowing that that means you need to calculate the clear zone, so calculating the area of this circle. So you get a mark for saying area equals pi r squared. So I know it's not maths, but you still get a mark for doing that, and it's worth doing that because if you go a bit wrong up here, you'll get some extra marks. Okay, and then if you get your ruler out, the closest thing I've got to a ruler is a tape measure, and measure these nice and properly, like so and like so. You do it properly, you will find that B has a diameter of 3.8 centimeters and A has a diameter of 4 centimeters. Okay, it doesn't matter whether you use millimeters or centimeters, but you need to make sure that you keep it the same for each, and then it's just a case of putting those numbers into your calculation here. And a common mistake to make is that you see R here is radius, so you need to half these numbers. So for A, you need to do pi times 2 squared. Okay, and for B, you need to do pi times 1.9 squared, because you're halving these numbers up here. So 2 divided by 2, halving it to get to 2, and 3.8 divided by 2 to get to 1.9. Okay, and then it's just a case of sticking those numbers into your calculator. So 2 squared, 2 times by 2 times by pi comes out at, you can just see it there, 12.6, and it's still in centimeters squared, and then 1.9 times 1.9 times by pi comes to 11.34 centimeters squared. Okay, so then compare the effectiveness. Well, this one has a greater clear zone, so it's more effective. It's worth just showing that you understand that. Great. So there is a very similar question to this in your assignment this week. Have a go at it. Make sure you're referring back to this video if you're not sure. Bye bye.